So I apologize for not being here in person. I understand the technical issues when we have a mixed Zoom and non-Zoom meeting are still plaguing us, and I hope this will move smoothly. I want to apologize for missing this fantastic gathering of all my favorite colleagues. My wife is now recovering from surgery. She finally decided to replace her knee, and this didn't seem like a good time for me to be zooming off, leaving her behind. Jean-Philippe deserves great applause for bringing this conference together under the inspiring rubric of more is different. Phil Anderson was my thesis advisor, and he has an amazing record of transformative ideas that have shaped physics and many other subjects. The work I'm going to be describing here is a work with a great number of colleagues, and you should think of my talk as describing their contributions, certainly more than my own. We are gathered here today to explain why nature is comprehensible. As Eugene Wigner asked, why does mathematics describe the world at all? And Phil Anderson gave a partial explanation. He said that very complicated systems, complex systems, can exhibit collective behavior that is comprehensible by ordinary people, and the laws that govern our economy or our ecosystem are every bit as fundamental as those of high energy physics. Today, I want to introduce a different type of emergence. And this new kind of emergence comes from a different mechanism. It's not due to renormalization groups and broken symmetries. It's due to a kind of interpolation theory, and we'll study with information geometry today. So the traditional physics approach, both in high energy physics and in condensed matter physics, is to have a systematic expansion from fundamental theories or base theories at high energies and short length scales through a series of systematic approximations. And in high energy physics, these approximations the theories get more beautiful as you go up in energy. In condensed matter physics, the highest energy theory, Schrodinger's equation, is a mess, and it gets more and more beautiful and symmetric as you raise the length scales and lower the energy scales. The kinds of methods that we're familiar with start with continuum limits, renormalization and coarse graining near critical points, and emergent scale invariance, asymptotic analysis for things like instantons and quantum tunneling, and symmetry breaking. And symmetry breaking and renormalization are shared with the high energy community. For other fields of science, I picked, for example, dynamical systems. They can see emergent behavior from very complicated systems using the Setter manifold theorem, using separation of time scales that allow them to have different descriptions for short and long times, and by and their material science and other fields have similar kinds of descriptions. Today, I'm going to talk about a different kind of emergence that doesn't have any of these features of symmetry breaking or coarse graining that we've been developing starting from applications in systems biology that I'll start with. And our group and this grand collaboration I've been involved with for some years have applied this to the electrical power grid, Mark Transtrom's work, particle accelerators, and other complex instruments, the cosmic microwave background radiation, and now a little bit into deep neural networks. And others have taken some of these ideas and applied them to living neural networks, nuclear matter density functionals. And there are lots of subjects that I would love to see used to test our ideas, such as climate science and economics and finance and interatomic potentials. So I'm going to start off by talking about sloppiness, and then I will go into information geometry, which is the tool we will use to visualize the emergent low-dimensional behavior that sloppiness hints at, and then I will go on to connect it with the ideas of emergence. So systems biology is filled with models with tens to thousands of proteins that communicate signals inside the cell. And we started many years ago with Kevin Brown and Rick Serione and others to look at a particular model, which was important in cancer biology, which had two kinds of external signals and receptors that went through a cascade of biochemical reactions to communicate a signal to the nucleus to tell it to reproduce or become a neuron. And they wrote down a series of differential equations, very unusual for biologists. And these nonlinear differential equations involve 48 unknown parameters. And the suggestion was that this was a well-understood system and we should be able to make predictions based on high-quality, thorough experimental work with 63 data points. And we offered to help out, but we were skeptical that we would ever be able to determine 48 parameters from 63 collective data points. In fact, we were unable to pin down the parameters. We could find the best fit, and then we did Monte Carlo around it, and we found that all the parameters varied. The best determined parameter had an error bar of a factor of 50. That's a 5,000% error. On the other hand, my cancer biology colleague was correct in the sense that we could still make predictions. So here's a prediction that happened to be correct, and that under a certain drug, the signals from the signals from one of the hormones would be transient over a period of 10 minutes, and the other one would be sustained. Now, the reason, the surprising thing is not that you can make a prediction, is not that you can make a correct prediction, it's that you can make a prediction at all, given that you don't have any control over the parameters. This is not robustness, where where the system has evolved so that the parameters don't matter. This is a feature of multi-parameter models with many parameters, and we will see, and it's due to the fact that only a few parameter combinations matter in these collective systems. So here is an example of 2 parameters out of many, and these are the contours showing that some parameters are more important than others. We call these stiff parameters and sloppy parameters. Most of the parameters you will see are sloppy, and we characterize it by the eigenvalues about this best fit. Now, I should mention that this is also very typical in the aspect ratio. You notice the axes here are very different. So if the screen is any size, to make this the proper aspect ratio, the horizontal axis would have to be stretched about 1 kilometer. The local quadratic form here determines what will become the metric in our metric tensor in our formulation later. The eigenvalues for this particular model span a factor of more than 1 million, which is common to lots of different physical systems. In this model, roughly each eigenvalue is separated by about a factor of 3, so it's logarithmically equally spaced, and that will be something we will return to. And it's not only observed in systems biology, it's in quantum chemistry. This is the quantum variational wave functions used in quantum Monte Carlo, which were the best ways at the time of deducing eigenvalues, excited states of small molecules. I will turn to the cosmic microwave background radiation, the Ising model, and things like that. Here is the particle accelerator at Cornell, and its eigenvalues, and these all share this feature of having very wide ranges of eigenvalues with only a few necessary to capture the main behavior. The question here is, how can we use this feature to develop emergent laws? This is not new yet. All of physics is based on the same idea, that we have renormalization group methods for studying the diffusion Ising model. We have continuum limits to study diffusion. In each of these cases, lots of parameters go into microscopic parameters in a physical system combined to give you the effective interaction strength between the particles, or the effective diffusion constant for the diffusion equation. And we can take our sloppiness, our eigenvalues, and generalize them appropriately to a probabilistic model using the Fisher information metric rather than the second derivative of the cost function, or the chi-squared. And we find that the microscopic model is not sloppy. If you know the probabilities of every spin configuration in a large system, you can predict what the microscopic interactions are, even if there are a bunch of long-range bonds. However, as you coarse grain, as we're familiar with, if you ask questions about the collective behavior, you discover just from information theory, without any renormalization group, other than the idea that looking at long length timescales, you discover a few stiff parameters and the same stiff parameters that you would get out of the renormalization group. and all the irrelevant parameter combinations become sloppy directions in the Fisher information metric. So it's now time to take a leap into differential geometry. This is a subject of differential geometry applied to probabilistic models. Our model had 48 parameters, and so its predictions of these 63 experimental data points become a surface, a 48-dimensional surface in the 63-dimensional space. By the way, feel free to ask questions during the talk. I would like to hope that there will be a little bit of interaction here. These model predictions, it's hard to look at a 48-dimensional manifold. So let's start with a 2-dimensional manifold, which won't be sloppy, but will illustrate a few important things, where I have 2 decaying exponentials, and I'm going to fit it to 3 data points so I can draw the model manifold in 3 dimensions. 2 decaying exponentials in parameter space have a stiff and a sloppy direction, if you like. And in data space, in prediction space, they form a 2-dimensional surface. This 2-dimensional surface, a few important things, have edges. If I take one of my exponentials and set it to infinity, then you get a simpler behavior that only depends upon one parameter. If you set it to 0, then it gives you another simpler behavior, one that decays to 1 rather than 0 at late times. And then if you set them equal, that gives you the third boundary. Those manifold boundaries, those simpler models, are going to be our way of taking the emergent low-dimensional behavior in our more complicated models and describe them with theories with simpler structure. The metric tensor is the Euclidean distance inside data space determined by the error bars in our experiment. And one other thing that I'm going to use later in trying to explain why we get low-dimensional hyperribbon behavior is that each time I take a measurement, say of y2 here, if I take a measurement at time t2, then it gives a slice of the model manifold at a constant value of the measured value of y2. And that slicing process is going to allow us to see what the geometry looks like of the model manifold. I will now tell you the model manifold will turn out to be what I would like to call a hyperribbon. A hyperribbon is something that's longer than it's wide, wider than it's thick, like a hypersphere or a hypercube, except grossly anisotropic. The thick directions, the long directions, are not the sloppy directions. They will correspond to very thin directions because you can move in sloppy directions without changing the behavior, and this is behavior space. Instead, the thick directions are traversed by the stiff parameters. And it's a remarkable fact that the eigenvalues, if you take their square roots, and if you take the eigendirections and use them to find the thicknesses in the 3 directions, in many directions, you take the geodesics along the eigenvectors from the best fit, you find almost exact correspondence between the widths and the square roots of the eigenvalues. So the hyperribbon has a hierarchy of widths that determine the hierarchy of sloppy eigenvalues. Now, here is the point where I try to explain, or I try to explain why it's a hyperribbon. This is work with Mark Transtrom. I keep forgetting to mention all my colleagues, but you remember when we measure a behavior, we get a cut of the model manifold. And each time I do a cut, I'm adding one more data point, and that reduces the possible predictions for all other times. Remember, each in this case, each measurement is specifying the model manifold at a new time, and thus is giving him another slice. And when you add a new measurement, interpolation theory tells you that the range of possible predictions at other times nearby is restricted by the biggest nth derivative of the function y, which is our prediction. And you can rewrite the nth derivative over m factorial in terms of the radius of convergence. You will remember from calculus, and if you take these time points and think of them as a range of times, then each time you add another data point, you reduce the range of possible behaviors in future directions that you might measure by a factor of delta t over r. So if you have enough data points to have 3 points per radius of convergence, you will get a factor of 3 every time you in width, every time you slice the model manifold. So we are finding that the hyperribbon follows from the analyticity of the model, the fact that it has a radius of convergence in whatever control parameters you're dealing with, temperature or time or other experimental conditions, and is a natural representation that does not demand symmetry breaking or anything fancy. This argument can be turned into a rigorous prediction that here is rigorous bounds on the shape of the model manifold for 3 different simple models that we could exhaustively study. Sums of exponentials that I think of as physics with radioactive decay, reaction rates in the simple collective model of chemistry, and very simple biology model for infection. Here are the model manifolds. Here are hyperellipsoid bounds, and with Catherine Quinn, with 2 mathematicians, Heather Wilbur and Alex Townsend, we're able to prove that a rigorous bound in which is the black curve and the dashed line, which shows that asymptotically it goes as a power law and pretty much saturates the behavior. So I would like to say that this gives you a new window into collective behavior, and it sort of reminds you of the typical engineering description. If you have a really messy problem, if you have a piece of metal that's been damaged by radiation or corrosion or something like that, rather than getting down and finding all the microscopic things that are going on as particles are smashing into their crystal structure, you take a bunch of measurements and you try finding the yield strength and the fracture toughness, and then you make predictions that you can build bridges with by fitting the data after multiple measurements, and trusting that the few measurements that you've made will tell you everything about other possible scenarios. So now I'm going to tell you a couple of things that we've looked at to use these hyperribbons. Hyperribbons clearly are an emergent thing. You have a low dimensional system that gives a good description of the material. And if you want a better description of material, you have to add only a couple more dimensions. But it's kind of abstract. How do you turn it into something concrete? So Mark Transtrom, this is not work that I was involved in. He did this on his own after he left. Developed a systematic way of coarse graining a complicated model. So you can think of the work we've done as explaining why complicated models have simple behavior, or complicated real world systems have simple behavior, justifying that we can assume that you get simple behavior out of real world systems. But Mark is taking the other attitude. You have a complicated model that works in describing the real world, but it's incomprehensible. Let's see if we can simplify it. So if most parameter directions are useless, why not remove some? Now, the problem was, at the time, the directions that were sloppy, the directions you wanted to remove were complicated combinations of each of the parameters. So here are all the parameters in the model, and here are the amplitudes that I would have to change, the logarithmic amplitudes I would have to change the parameters by to move along the sloppy direction. The stiff directions are also incomprehensible. So it's like random matrix theory. But if Mark was taking geodesics to find the width of the model manifold, and his criterion for stopping was when this sloppy eigendirection became simple. And it dawned on him at some point that that was a suggestion that the edges of the model manifold, like in our two exponential problem, were simpler models. So this might be a model where two reaction rates, forward and backward, both diverged, got faster and faster as you approach the edge, until at the edge you can just assume that those two reactions can be replaced by an local equilibrium between reactants and products. And he took this procedure, and then he would go to the edge of the model manifold, reoptimize, go to the edge of the model manifold, reoptimize, each time dropping one parameter. And he did that 36 times, and he ended up with a 12 parameter model that described the behavior just as well as the original one, or basically almost as well as the original one, and was much less sloppy. There's more. So here's that bewildering network that my cancer biology friend could speak of as feedback loops, but to ordinary humans it was hard to discern these nice feedback loops and side branches and things. without having an expert, wise and it had 48 parameters and 29 ODEs, and it was sloppy. Here's the reduced model. You can easily see it just fleshes out the simple mechanisms that are controlling things. The different proteins are replaced by collective proteins. The different reactions are replaced by a much simpler set of differential equations. The reduced parameter fits all the experimental data almost as well as the original. That's how he decided to stop at 12 parameters. And each of the collective parameters is an explicit function of the original parameters. So if you believe your original model is correct, you can use it, this reduced description, to predict the future. This is just an amazing new technique that he's been now applying for power systems and other systems. Now, to conclude, I want to describe a remarkable new method of looking at high dimensional models, both in physics and in machine learning that we've looked at, that bypass the curse of dimensionality. Curse of dimensionality is a big deal in data science, and in machine learning. You have these huge data sets, and you have enough, and they have such high dimensional behavior that sort of every two data points are orthogonal to all the others, and trying to find low dimensional behavior in a situation like that is challenging. We have a similar problem that we stumbled into, that if you have a model where you know the behavior may be low dimensional, but the probability distributions that you're generating are very high dimensional, then your probability distributions become orthogonal. And how do you visualize it? So, for example, the Ising model, you know it only has two parameters. That you have the external field and you have temperature. But the Ising model has prediction if you have n spins of a point in the 2 to the n dimensional probability space. I won't go into details, but the key problem is every time you change the parameters a little bit, if you have a 1,000 by 1,000 Ising model, you have 2 to the 1 million dimensional space. And in that space, you can tell the difference between two different external fields or two different temperatures with a relatively straight, just staring at a picture. Those probability distributions rapidly become orthogonal. And so thinking about it in any systematic way involving probability space, every new parameter set is orthogonal to every other one. We figured out a way of bypassing that using replica theory, taking the limit of zero data and applied it to the space of all possible universes. This is a lambda cold-dark matter model applied to the cosmic microwave background radiation. We've applied it to the Ising model, a new variant of this same system by Han King Kant. This is again Catherine Quinn's work, and to machine learning. And let me tell you, this is very new work.
Jim,
with collaborators.
Jim, can you hear me?
Chaudhry. Yes.
Can you wrap up in 5 minutes so we have time for questions?
Oh, this is the last slide.
Great.
So we have Jialin Mao and Pratik Chaudhry. We have we are looking at deep neural networks. These are million parameter models fit to hundreds of thousands of data points. In this case, it's 50,000 images and 10 categories, and you start with complete ignorance. So here is an ensemble of neural networks that we're looking how they're trained, and as the training process occurs, a given neural network will go through a bunch of probabilities. And notice I'm plotting these in a three-dimensional space. The probability distribution describing the current snapshot of a neural network is the probability that that neural network attributes to each of 50,000 images in the 10 categories that it's trying to sort them out into. It's going from ignorance to knowing which category each whether it's a bird or a frog, and 3 dimensions is enough to capture 77% of the variance. So neural networks, as they learn, produce trajectories in a space that acts like a hyperribbon. We're pushing this forward as we speak. So I hope I've entertained you briefly, given you some of the enthusiasm that our group has had in pursuing this sort of new aspect of emergence of how complex systems that exhibit comprehensible behavior. The comprehension may not be due to a systematic derivation from the underlying microscopics. The underlying microscopics may not have simple structures that are, but it may, just by having a little bit of analyticity in its behavior, lead to interpolation rather than field theory making things work. Thank you.
Thank you.